All right, hey guys, this is not 7-2, this is 7-1. So go ahead and set a timer for 5 minutes and then push play and we can get started. Okay, name the 4 transformations that preserve the length of each side of a figure. That would be a translation, rotation, reflection, and a glide reflection. And then the only one that does not preserve distance, so it is not a rigid motion, that is a dilation. So then which of the following does not preserve distance? That would have to be this one. That's the only one that is a dilation because it has a 7 being multiplied to the x and the y. Whenever you are multiplying by a number that is not 1, then you are dilating the figure, either making it grow or shrink. Number 4 is an algebra review problem. We're using substitution. So this bottom one, it already says t equals. So we're going to replace t with what t is equal to. So negative 6k minus t is equal to 13. You have to plug in t with the parentheses in this case because of that minus sitting there. I'm actually going to plug it in black so you can really see what we're doing. That negative has to distribute to both things here. So negative 6k, a negative distributed to a 3 is negative 3. The negative distributed to the negative 2k is a positive 2k, and then equals 13. Combining like terms from there, I see negative 6k and positive 2k. That makes it negative 4k. Bring down the negative 3, bring down the equals 13. We can add 3 to both sides. And we get, I'm gonna move over here. Add 3 to both sides and we get negative 4k is equal to 16. Then if we divide by negative 4 on both sides, we're gonna get k is equal to negative 4. A positive divided by a negative is a negative, and 16 divided by 4 is 4. All right, moving right along. I'm going to keep that on the screen for just a little bit, just in case you are still writing. We are going to move into dilation. So we actually have talked about them a lot, so this is not going to be a super hard section. A dilation, that's your first blink, is a transformation that changes the size of a figure but not the shape. We've already talked about this. This is like dilating your eyes at the eye doctor. Your pupils get bigger and then they end up getting smaller. They go back to their normal size, right? A dilation is just a change in size. Now, it cannot change the shape. So this second example over here, that is not a dilation because the shape has actually changed now. The image and the pre-image of a figure under a dilation are, I guess similar is what we're going for. Oh yeah, it would have to be similar. Chapter 7 is actually on similarity, so that would make sense. Okay, a dilation, it's gonna be notated with a capital D, is a transformation in which the lines are connecting every point A with its image A prime. So that means from the center of dilation, P, it can connect A and A prime. If you connect B and B prime, it's also going to pass through P, and if you connect C and C prime, it's also going to pass through P, that center of dilation. So P is called the center of dilation. Typically it's going to be at 0, 0. Every angle is going to be congruent to its image under a dilation. All the angles are going to stay the same. It's just the side lengths that change. Next is the scale factor factor just means multiplying by something. So scale factor is just the number that we are multiplying by to get the final product or the final image. So if we ever want to find the scale factor, we can use this right here. We can say the image divided by the pre-image. That will give us the fraction or the whole number, depending. It'll give us that scale factor. Okay, so for example, in this case right here, if this length ends up being 2, and this length originally was 1, then we can do the new divided by the old, and that's going to give us that scale factor, which is going to end up being 2 in that case. So then our rule would be 2x, comma 2y. We actually can use it. We can actually use this concept for each of the coordinates as well. The coordinates will just multiply 2 to the x and 2 to the y if the scale factor is 2. Now a reduction, let's say that now this is 1 and this is 2, but look at where the new one is. The new one is the one with the primes, right? So if we're doing new divided by old, new divided by old, now we have a fraction of 1/2. That's between 0 and 1, or it's less than 1, which means that we are going to be shrinking. We are growing if we're multiplying by a number bigger than 1. We are shrinking or reducing if the number is a fraction that's less than 1. Flip it over to the back. Let's go ahead and plot these points. So 0, 0, -1, 2, and 3, 4. This is K, and this is L.
Hi, Ms. Krausman.
Hi.
Happy New Year.
You too. Okay, so what we're doing for the scale factor, if the scale factor is 2, we're just going to multiply by 2 to everything. Okay, so that's going to end up at 0, 0. This one's going to end up at -2, 4. We're just multiplying by 2. And then this one's going to end up at 6, 8. We're just multiplying by 2. So -2, 4 puts K prime right there. And then 6, 8 puts L prime right here. And if we connect all of those, we'll see that the shape itself just grew. This angle still stayed the same. And if we were to find this angle here, it would be the same as this angle down here. So it created 2 similar figures, meaning they're the same shape, just a different size. Got 2 times bigger. Okay, so pause your video and just take 2 minutes. Just take 2 minutes on this one and see how far you can get. Okay, A is at 0, 0, B is at 0, 6, C is at 6, 3. A, B, C. All right, our scale factor is 1/3. So we are multiplying by 1/3. That is the same thing as multiplying by 1 and then dividing by 3. Multiplying by 1 doesn't do anything. So this is essentially the same thing as just dividing by 3 to everything. So if we divide by 3, 0, 0 is going to remain 0, 0. 0, 6 is going to be 0, 2 if we divide by 3. And then 6, 3 will become 2, 1. So 0, 0, 0, 2, and 2, 1. So now our new image looks like that. It was reduced by 1/3. Now, keep in mind that doesn't mean the area of it has reduced by 1/3. It means that each side length has reduced by 3. Okay, so population density. This one's a little strange. Population density is going to be, think about what density actually means, right? If we're talking about the population density of Orlando, we're talking about the number of people per some kind of area, per square mile, per whatever it might be, okay? People per area is what we're looking for. So, I think that this was a typo over here. This is supposed to say miles. It's not supposed to be meters and miles. I'm just trying to teach you population density. We don't have to change a bunch of units. So it says that Mott County is divided into 4 equally sized administrative zones, zone 1, 2, 3, and 4. Each zone is a dilation of the county as a whole with a scale factor of 1/2, meaning that if the entire thing is 48 by 39, then each of these is going to have lengths that are half of each of those, right? What would the population of each zone, what would be the population of each zone if it has the same population density of the county as a whole, meaning all of these people are equally distributed between the 4 counties? So first of all, we're going to find the area of Mott County. So area is just base times height. So 48 times 39, which I'm going to need a calculator for. 38 times 49 is going to give us 1,862. And remember, this is area, so our units would be miles squared. All right, population density. It's people divided by area. So the people, that's 388,643. I got that from right here. That's the population. Divided by the area, which is 1,862 miles squared. So 388 divided by, 388,643 divided by 1862 gives us about 200 and, I'm going to say 209 people divided by miles squared, or people per mile squared, or people per square mile. I rounded up to 209 because you can't have 0.7 of a person. All right, find the area of one of the administrative zones. Find the area of one. Well, if the entire area was 1862, then one of them you just have to divide by 4, right? Or you could do half of 39 times half of 48, either way. But I'm going to do 1862 divided by 4, since there are 4 administrative zones. 1862 divided by 4 gives us 465.5 miles squared. And you can have 0.5 of a mile, so that looks fine. Find the population of each administrative zone. Find the population. Oh, okay. So if there is a population density of 209 people per square mile, if we multiply that by the number of miles that we're dealing with, 465.5 miles squared, look here. Now there's a mile squared on top that cancels out with a mile squared on the bottom, and we are just left with people. It's asking find the population, so people is what we can end up with. So 209 times 465.5 is going to give us 97,000 280, 89, so 90, because it was 0.5 people. Something like that. And I'm curious, if we multiply that by 4, then it will be approximately what the population was for Mott County. There's a little bit of error in there. All right. So let's take 5 minutes and try this exit ticket. It has population density problems, and then it also has a scale factor problem. So start your timer for 5 minutes and then unpause your video when you're ready to go over it. Okay, number 1, using the population density information above, suppose the population of zone 1 is 102, let me change my color. Zone 1 is 102,981 people. So then what is the population density of zone 1? Well, population density is the number of people, so 102,981 divided by the area. So the area just of zone 1 would be the 465.5, because that is the area of one administrative zone. So 102,981 divided by 465.5 gives us a population density of 221. I'm going to keep it at 221 people per square mile, because in the numerator we had people, in the denominator we had miles squared, so people per square mile. So then what would the population density of 2, 3, and 4 be if we take that as a whole? So the population, let's just start there. The population would be 388,643 minus 102,981. Okay, 388,643 minus 102,981. That gives us a population of 285,662. So 2, 3, and 4 combined, that's the population. And we're going to divide that by the area of zones 2, 3, and 4 put together. So the area of 2, 3, and 4, that would be the area of one of them, so 465.5, but times 3, because there are 3 zones. So I'm doing 465.5 times 3 in my calculator for the area. And I got a total area for those 3 zones of 1,396.5. And let's see what that gives us. 285,662 divided by 1,396.5. And we get a population density of 204. I'm going to round that up to 205 people per square mile. So if the population density is higher in one zone, because remember if they all were the same, it was 209. If the population density is higher in one zone, that's going to lower it. Ooh, where'd my voice go? It's going to lower it for all the rest of the zones. So glad that little voice crack is on video. That's great. Okay, number 2, graph the pre-image and the image. So the pre-image is going to be what they already gave us. So 0, 0, -2, 4. That's K. And 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. And that's L. The scale factor is 1/2, so that's the same thing as multiplying by 1 and then dividing by 2. If you multiply by 1, nothing changes. So we essentially could just divide by 2 to each one of these. Our scale factor is dividing by 2. So that's going to keep us at 0, 0. and then it's going to put us at negative 1, 2, and then it's going to put us at 3, 4. So negative 1, 2, and 3, 4. So that would be our image, K prime, L prime.